Good evening. Today I'm going to go ahead and start with mathematical methods in economics. From now onwards, I'm going to have two classes every day. One is going to be on maths, which I'm going to start from today. And the other class is going to be on the microeconomics, which we are continuing from where we have left, and we would be taking it from there only. So, I would be sending out the schedule very soon, but please fix this time from 7 to 8 for mathematical methods and economics from today onwards. Now, to begin with, the first concept that we have to kind of try and understand whenever we talk about set theory is what are sets? Now, set theory is essentially the first and foremost topic whenever it comes to understanding what are functions to begin with or what are relations. Now, ideally, all of us go out and, do shopping every month for, our home. And we kind of end up buying a lot of things. Like, for example, when I go to a supermarket, like, for example, if I go to Big Bazaar or if I go to, let's say, any other place, what do? I'm going to go ahead and I'm going to buy some fruits. I buy some vegetables. I go ahead and I buy something which is a frozen food. I go ahead and I buy something for my dishwashers. I go ahead and I buy something related to, let's say, floor cleaner, something related to, let's say, clothes cleaner, etc. Now, what really happens is that what you would notice is that not all of these things are placed together. And when I say that not all of those things are placed together, we would see them in different sections. There would be a counter which is only going to be there for fruits. There is going to be a counter which is only going to be there for, vegetables, etc. Why? Why is that there? Why can't they just put everything at the same place? Because ideally, we want to save time and we want to save money. So, just try and understand that everything that you observe, whether it is anything related to a basic human psychology or whether it is being deep dived into microeconomics, every place has concepts which are maths oriented, and every place we are going to go ahead and use some aspects of mathematics. So, ideally, what we follow at all of those supermarkets is making sense. We keep a place only for fruits, where I may have apple, oranges, etc., etc. But that is a set which is only for fruits. We keep a place only for vegetables. We keep a place only for dishwashers, and so on. So, the question that arises is, what is a set? A set is a collection of objects. For example, collection of fruits is a set of fruits. Collection of vegetables is a set of vegetables. Collection of maybe other things are set of those things. So a set is a collection of objects. Now, there are various things that we have to understand in the definition of sets. And what are those? A set is a well-defined, and I will go through each word of this definition together with you. So a set is a well-defined collection of distinct objects. All of these things are going to play a very important role in the definition. So what are we saying? We are saying that set is a well-defined. We have to be able to define the set well. Collection. It has to be a thing where things are getting collected. There is a place where only fruits are getting collected. There is a place where only vegetables are getting collected. So a set is a well-defined collection of distinct means unique. They are unique in nature. So unique objects. What are objects? Objects are my fruits, for example, apple, mango, banana, etc. Objects in set of vegetables will be broccoli, cabbage, onion, etc. Objects in set of clothes will be kurta, pajama, etc. So objects, what does my set consist of is called an object. These objects that we are talking about are also called elements. So any object of the set is also known as an element of the set. So, you know, when I talk about apple, mango, etc., they are objects of my set of fruits, or they are also elements of my set of fruits. Now, you know, give me some time and I really want to kind of focus in detail on what is well-defined, collection, distinct, and objects. To begin with, let us go through a few examples of what is a set. So a set can be set of fruits, a set can be set of vegetables, a set can be set of numbers, set of natural numbers, set of odd numbers, set of even numbers. A set can be anything which has a collection of objects to it. Now, very shortly, I would be going ahead and redefining this thing. So although for now, I am saying that this is a collection of objects, I will also go ahead and define a set without collection of objects. But I will go ahead and call that as an empty set. So I can very well have a set which does not have any object in it. But if something does not have an element in it, if it does not have an object in it, it becomes an empty set. But if a set has an object in it, then that's the usual set that we are talking about. Okay. Now, sets are basically denoted by symbols. Always remember that a set will always be denoted by a capital alphabet. So, you know, you will never see, you know, I will never go ahead and say that this is a set, or this is a set, or this is a set. This is never going to happen. We will always denote a set by a capital alphabet. But the elements of the set, they will be denoted by small alphabets. So I can go ahead and say that there is this element X that belongs to the set A. This can very well be done. So whenever you see small alphabets, they always represent elements. Small alphabet, they always represent element of the set. Whenever you see capital alphabets, they represent the set in itself. Now here, you might be seeing this real sign here. This just says if something belongs to something or not. So this is a sign that is used to say this belongs to something. So for example, 1 belongs to the set of natural numbers. 2 belongs to the set of natural numbers. So, you know, this sign simply tells me if something belongs to something or not. Now, let's go ahead and look at one of the sets. So what I'm doing here is I'm saying A is a set, and this set A consists of first 4 natural numbers. So I'm going to go ahead and represent A by a capital alphabet because that represents a set. These parentheses are used to represent set. You will never ever see any set which is represented like this. I will never write this, that A is 1, 2, 3, 4. I will never do that. I'm not making a vector here. I'm making a set here. And a set will always be given by these curly brackets. So, I am saying A written in capital is a set, and it consists of the first 4 elements, first 4 natural numbers. So I say 1, 2, 3, and 4. Now, I'm going to go back to the definition of sets, that set is well-defined collection of distinct object. And now what I'm going to do is, I'm going to focus on the word distinct. What is it? What does it mean to be a distinct element? So an element is distinct if it is only coming once in the set. And to remember this, I'll again give you a very, very good example from the, from the supermarket that we visit. Now, for example, I go to different corners of the supermarket, and we see a corner which is solely dedicated to fruits. And now what do I observe? I observe that, okay, within this corner of fruits that I have, there is this. So let's say that this is a set of fruits in the supermarket. I see that, okay, here they have kept bananas. Here they have kept apples. Here they have kept oranges. Here they have kept mangoes. Here they have kept grapes. Have you ever seen that they are keeping the same type of bananas at 2 different places? No, right? We will only see that these bananas are coming once. Apples are coming once. I will never ever see that within the same display, one tray is here and one tray last at the last, but they refer to the same fruit. That would never be the case. Exactly is the point with sets. The elements in the sets are unique. And by unique, I want to say that these elements, they come only and exactly once. I do not want these elements to be repeated more than once. So, for example, let's take these 2 sets. In the first set, I see that 1, 2, 3, and 4, all of these elements are coming exactly once. This is a set. Let's look at the second set. I see that 1, 2, 3 are coming once, that is fine. But 5 is coming twice. Because 5 is repeating twice in the set, this is not a set. Each element should come only once in the set, whatever be its frequency. Even if I want to, even if I say I have 5 kgs of apple right here, I am just going to represent it by 1 in the set, that I have apple, I have mango, I have bananas, etc. So I am never ever going to represent the same element twice in my set. This is what is the definition or meaning of being distinct. You only see each element coming exactly once in the set. Now, again, let's go back to the definition. Set is well-defined collection of distinct objects. And now I want to focus on the word well-defined. Now, when I say that a set is well-defined, I am saying that each element of the set is defined, which means that there are only two things that are possible with the set. Either an element belongs to the set, or an element does not belong to the set. In that sense, my set is completely defined. Either I will have the element defined in the set, or I will not have the element in the set. You cannot have both at the same time, and you cannot have neither also. So let's take an example here. So for example, I tell you that I am referring to, a set of first four natural numbers. Now, if I'm referring to the set of first four natural numbers, then I know that my set, supposedly I talk about the same set, my set A is first four natural numbers. Now I ask you a very simple question. Does 5 belong to A? The answer is no. I cannot see 5 here. This is just first four natural numbers. Does 3 belong to A? The answer is yes, it belongs to A. So in that sense, because I have been able to tell whether an element belongs to the set or not, I am saying that this is well defined. Let's take another example. So, B is a set of first 5 odd natural numbers. So I go ahead and write 1, 3, 5, 7, and 9. And now I ask you the question, does 2 belong to the set? No, it does not belong to the set. Does 5 belong to the set? Yes, 5 belongs to B. So because I have been able to clearly explain whether something belongs or does not belong, this is clearly coming from my set. The set is well defined. I clearly know which elements belong to the set and which elements do not belong to the set. Let's take another example. For example, I ask you this question. Consider all the students that are attending this class today. All of us. Okay. Is this a set? Well, yes. My set will consist of all of us, right? So it will consist of Kunal, it will consist of Viblu, it will consist of Vijeta, etc. This is my set. Now I ask you, is this set distinct? The answer is yes, it is. Because I see each of the element only coming once. I don't see any element coming twice. Is this well defined? The answer is again yes. Because if you tell me that, person A, B, C, does person A, B, C, does he belong to this set A? My answer is no. Does person, maybe does Arav, does he belong to the set? My answer is yes. So just by knowing how my set is defined, I am able to tell you whether an element is part of my set or not. And in that sense, my set is definitely well defined. Now, the next question that is asked is, how do we represent a set? See, a set can have huge number of elements. Now, here I was just dealing with first 4 natural numbers or first 5 odd natural numbers. That may not always be the case. So, there might be chances that we may have huge number of elements. For example, we may have a case where I'm dealing with all the natural numbers. Then in that case, what will happen? It starts from 1, 2, 3, but it goes till infinity. Or I may have a case where I have a set of 100 students in the same class. Again, in that case, I cannot go ahead and start defining the set that, A is A, individual A, individual B, individual C, D, and so on. This is not possible. So, whenever you have a set which has huge number of elements, that is where I'm going to go ahead and I can use a certain way to represent this set. Now, what's the way that I can use? Let's look here. So I am saying, define my set A. What is A? A takes care of all the students. A can only consist of students, but which students? Only those students which belong to this class. So what I'm going to do is, here I'm going to give the condition of the set. And here I'm going to say the condition of the element. I have to make sure that anybody who is part of this set is a student, but I have to also ensure that that student belongs to my class. Only then it is a set of students who belong to my class. Let's take more examples. So I want to understand the set of odd natural numbers, which means my set B can consist of natural numbers. That's the bigger thing. Like student is a broad horizon, right? All the students. But among those students, which students? Who attend my class. Similarly, all the natural numbers. But among that natural number, which natural number will be in my set? Only those which are odd natural numbers. So, the condition related to which kind of natural numbers will be there will be given here. Similarly, condition related to which kind of students, that will be here. So, for example, I tell you that I want all, and I want you to try this once. I want all those natural numbers which are perfect squares. Which means I want all those natural numbers which are, when you find out the root, you get a natural number only. So, for example, when I find out the root of 9, I get 3. When I find out the root of 16, I get 4. But when I find out the root of 2, I get 1.414. I don't want that natural number. So what I want you to do as an activity is try this question once. I want you to find out the set of all natural numbers, but those natural numbers should also be perfect squares. Okay. Now, if we understand this well, if we understand what is a set, we have to also understand that there are different types of set. And by types, I mean that we have different denotions of the set. We can denote different kind of sets by different alphabets. Now, the first kind of set that we want to deal with is N. N is usually used to represent any natural number. So the set of natural numbers is represented by N. 1, 2, 3, 4, and so on. Now, here I want to also kind of focus a bit on whole numbers, which usually people kind of don't do. So, whole numbers. are my natural numbers, but they also include 0 in it. Okay, so whole numbers are natural numbers inclusive of 0. So 0 and natural numbers together form my whole numbers, which means that I can write the set of my whole numbers starting from 0. 0, 1, 2, 3, 4, etc. Otherwise, it's the same. Very, very rarely will we be talking specifically about whole numbers. Usually, we will consider, natural numbers is the definition that I would be using. Now, let us go ahead and talk about integers. What are integers? Integers are all negative numbers, 0, and positive numbers. Integers would be given by Z. This is what I'm going to use for integers. If I have to tell you to give me a set of only positive integers, I'm going to use Z plus. So Z plus is literally nothing but natural numbers, right? Because I have gone ahead and I have eliminated all, because I've gone ahead and I have eliminated all the negative numbers and zeros. So, Z plus is ideally nothing but my natural numbers. Now, the next thing that you have to understand is the set of rational numbers, which is represented by Q. What is the set of rational numbers? Anything which is of the form P by Q, such that Q is not equal to 0. See, anything by 0 is infinity. I cannot define that. So Q should not be equal to 0. That's the first thing. The second thing that you have to understand is that I should be able to represent it in the form of P by Q. Now, for example, if I take root 2, and if I find out the value of root 2, you will notice that this is 1.414 something, something, something. But you cannot represent it completely in the form of P by Q. But if I give you the example of 0.2, then I can simply write this as 2 by 10. So 0.2 is a rational number, but root 2 is not a rational number. Now, notice that every natural number is automatically a rational number, because natural number can be 1, 2, 3, etc. And I can write 1 as 1 by 1, 2 as 2 by 1, 3 as 3 by 1. So it automatically becomes a rational number. Similarly, notice that even if it is a Z, so maybe if I say -3, -2, etc., then -3 can also be written as -3 by 1. -2 can be written as -2 by 1. 4 can be written as 4 by 1. So even the set of integers are rational numbers. Now we go ahead and we define something which is known as a real number. What is a real number? A real number is a set of rational numbers and irrational numbers together. Remember that rational number is anything which is of the form P by Q, but rational number automatically includes natural numbers and it also includes integers. So real number indirectly includes natural numbers and integers. And irrational number is any number which cannot be represented in P by Q form. Cannot be represented in P by Q form. Okay. So these are your irrational numbers. Now, just like we did Z plus, we can also do R plus. Okay. So R plus will be the set of positive real numbers. If I do not consider my negative real numbers, only positive real numbers, that becomes R plus. I introduce a new term then, which is known as C, and C is for all the complex. So complex numbers are a set of real plus non-real numbers. What are non-real numbers? Non-real numbers are any numbers which are imaginary numbers. So anything that has an iota with it. For example, 5 plus 6 iota, 3 iota, 7 iota. If you have an iota, this is known as iota, which is imaginary. If you have an imaginary part to the real numbers, they become non-real numbers. Now, what I have done is I've gone ahead and represented this entire thing with the help of circles so that you understand this better. Now, please see this. We began with a set of natural numbers. And then we went ahead and we said that, natural numbers plus negative numbers. So we already have natural numbers. But if you also include negative numbers to them, it becomes integers. Any integer can be written in P by Q form. Any natural number can be written in P by Q form. But I may have fractions also. I may have 1 by 2, minus 2 by 3, minus 4 by 5. So all those fractions included will give me my rational numbers. I may have either a number being rational or a number can be irrational. A number is irrational if it cannot be written in P by Q form. For example, root 2, for example, minus root 3, etc. If a number cannot be written in cannot be written in P by Q form, it becomes irrational number. Whether a number is rational or irrational, both of them are called real numbers. Then we have something which is known as imaginary numbers, which has iota in it. Whether a number is a real number or whether a number is an imaginary number, both these things together form complex numbers. So complex number has this complete circle in it of real numbers. And then complex number also has these imaginary numbers to it. Now, once we understand this thing well, we want to go ahead and understand two important definitions of two types of sets. The first is known as an empty set. An empty set is given by phi. It's called phi. Okay. And what is a phi? It's represented like this. And this consists of no element. So if my set is empty, it's blank, zero element, no element is there, then it's an empty set. Now, let's consider this. If I write A like this, and I don't write anything in between, then A is an empty set. But if I write A like this, A has an element which is 0, then A is not empty. It has an element in it whose value is 0. So please understand the difference. Empty means no element in it. If you have an element in it, irrespective of it is 0 or any other number, then it is a non-empty set. It is not empty. The other thing that you have to understand is called a universal set. A universal set is all the elements together. So, supposedly, I tell you that A is a set of 10 natural numbers. Then universal set will be all the natural numbers. If I tell you B is a set of first 5 real numbers, then U will be a set of all the real numbers. So universe is always, as the word suggests, universe. It's the set of all real numbers. Or my universe can be C. So it will be the set of all complex numbers. Or my universe can be all the students in the class. And my set can be top 5 students of my class. Right? So universe is all the elements together. That makes a universe. Now, the next thing that we have to understand is known as a subset. What is subset? To understand what is a subset, we should understand the definition of it mathematically first, and then I will explain you. So please understand this definition first. If X belongs to A implies that X belongs to B, then A is a subset of B. So for example, if I tell you that A is 1, 2, 3, 4, B is also 1, 2, 3, 4. If this is the case, then A is a subset of B, because whatever is coming in A is coming in B. Now understand this thing. Suppose C is 1, 2, 3, 4. B is 1, 2, 3, 4, 5. Then C is a subset of B. Because whatever is coming in C is definitely coming in D. Then C is a subset of D. Supposedly, I tell you that E is 1, 2, 3. F is 2, 3, 4. Then E is not a subset of F, because whatever is there in E is not there in F. So we say that A is a subset of B only if all the elements that are present in A are sure present in B. You should not have any element of A not being a part of B. It has to be a part of B for any element you pick up. If I pick up an element in A, it has to be present in B. I pick up another element of A, it has to be present in B. Then A is a subset of B. Now, from subset, we go to the definition of proper subset. Now, if A is a subset of B, it's written like this. This is just saying subset. If A is a proper subset of B, then it is written like this. This is known as proper subset. Now, what is proper subset? Proper subset is when all elements of A has to be in B, because that's the definition of subset. But supposedly, there is an element of B which is not present in A. In that sense, I'm saying A is a smaller set. B is a large set. I'll talk about cardinality slowly, but just understand. A is a small set. B is a large set. A is completely in B, but B has more elements also. So this is B. This is A. All elements of A are in B. But there are some more elements in B which is not there in A. Then we say A is a subset of B. So please see this. Y belongs to B. And I should be writing Y small just to be kind of sure that it's an element. So Y belongs to B such that Y does not belong to A. Then A is a subset of B, but a proper subset. Let's see this from the examples. So consider this example, example 1. Okay. A consists of 1, 2, 3, 4. B also consists of 1, 2, 3, 4. B doesn't have any additional element. So whatever A has, B also has that. But B doesn't have anything extra. So I cannot say that A is a proper subset of B. I cannot say this. I can say A is a subset of B, but I cannot say anything about being a proper subset. Now consider this example. C has 1, 2, 3, 4. D also has 1, 2, 3, 4. But D has more. 5 belongs to D, but 5 does not belong to C. Then C is also a proper subset of D. So we say something to be a proper subset if it has one element, the bigger set has at least one element which is not present in the smaller set. So, you should write down this thing. Just try this out. I am telling you A is first 4 natural numbers. B is first 10 natural numbers. And you have to tell me these two statements. Is A a subset of B? Second, is A a proper subset of B? Okay. All right. Now, let's go ahead and do an important property right here. So, just understand this thing. Empty set is a subset of every set. Empty is nothing, right? So, imagine this thing. Supposedly, I have a set A. And let's say that this set A is 1, 2, 3. Suppose I pick up A, I pick up 1 and I remove it from the set. I pick up 2 and I remove it from my set. I remove 3 also from my set. If I remove all the 3 elements from my set, then also A will still be an empty set. Even if I have removed all the elements from A is still an empty set. If A is still an empty set, which means it always had this empty belonging to itself and it had more things to do with it. So in that sense, empty set will always be a subset of any set. Any set. Now, if A is not empty, supposedly this, A is not empty, then A has that empty, but it also has more elements to it. Because A is not empty, it means A is a bigger set, A has more elements in it. empty is 0. It doesn't have any element in it. So in that sense, if A is not empty, then empty becomes a proper subset of A. So we can say the following. Supposedly I give you two things. I tell you that I have two sets. This is A, 1, 2, 3, and this is B, and B is an empty set. So in the first case, empty is a subset of A, but empty is also a proper subset of A. So empty is also a proper subset. In the other case, empty is a subset of B, but empty is not a proper subset of B, because B doesn't have any additional element over and above empty. And to be a proper subset, you should have at least one additional element in the bigger set, right? Which is not there. So therefore, we say that if empty is a subset of A and A is not empty, then empty is a proper set of A, proper subset of A, right? Now, let's introduce something which is known as a superset. See, we understood that supposedly this is a large set B and this is a smaller set A. Is all the elements are in B. Then we say that A is a subset of B, right? But we can also say that B is a superset of A, just the opposite of subset. So we can say that A is a subset of B and B is a superset of A. These are just different ways of saying exactly the same thing. Now, one thing that I want to also highlight here is something related to the universal set. See, universal set is a bigger set, right? Universal set has everything in it. So if universal set has everything in it, then every set will be a subset of the universal set. Because universal is literally everything together. It's the biggest set possible. So every other set will be a universal set. So we say that A is any set, U is a universal set, then A is a subset of universal set. Okay, now I'm going to go ahead and ask you a very small question from sets. So I am saying the following. I am saying that A is a subset of B. I'm not using the word proper. I'm saying A is a subset of B. And I'm saying that B is also a subset of A. Then what do you imply? What do you think will happen if both are subsets of each other? So just consider this, very simple. If A is a subset of B, then all elements of A should be present in B. Whatever is in A, it has to be there in B. But if B is a subset of A, then all elements of B has to be in A. Right, same elements, absolutely. So if all elements of A are in B and all elements of B are in A, it means none of them have an additional element. Whatever, suppose A has 1, 2, 3, 4, and B has 1, 2, 3, 4, 5, then in this case, B cannot be a subset of A, right? Because B has more element. For B to be a subset of A, B should also have the same elements. So if A is a subset of B and B is a subset of A, we can say that A and B are equal. The two sets are exactly the same. They have all the elements of each other. And I want you to write this mathematically. So, you should be able to write that if A is a subset of B, then if any element belongs to A, it also belongs to B. If B is a subset of A, then any element that belongs to B also belongs to A. This is true for any X. This is true for any Y. So from these two, we can say that A and B are equal. You should be able to represent things mathematically. Okay? All right. We'll continue tomorrow. Thank you.